Okay, then I start. So welcome everybody to today's Cubic Tech Talk, and welcome especially Jerven Bolleman. I'm really happy that we could that we can welcome you for that first virtual tech talk. So we usually have these series of talks, like we aim at having like once per month a tech talk where we discuss latest technology around bioinformatics, around high throughput technologies. However, we didn't have one since we all moved to home office. So I'm really happy about this first fully virtual Cubic Tech Talk. So I say a few words about Jerven. Jerven did study bioinformatics in Groningen in the Netherlands, where he graduated in 2007. Then he worked in a company as a software engineer for a while, before taking up the role as a lead software developer at the Swiss Institute for Bioinformatics, where he is still working today. He has done some very important work around UniProt, worked on Blast user interfaces, and lately also worked on Sparkle endpoint implementation that we also started to work on quite a bit. And worked on other important software applications. And with that, I'm really looking forward to your talk.
So, hi everybody, my name is Jerven. I am quite pleased to give a virtual talk. I hope the sound quality is good. If not, please shout into the chat. So, my title is Interoperability in the Sciences. It's in the semantics. And basically, I'm going to talk a little bit about the SIB, the Swiss Institute of Bioinformatics, and then I'm going to go into lots of technical details. I normally work on www.interoperability.org, so most of it is the front end, the search engine, storage layer, making sure that it all runs relatively smoothly. And besides that, I also do a lot of RDF and Sparkle, because I think that is a really nice extra thing that we can do. So SIB. So it's a confederation with lots of different groups at different institutes. It's a very Swiss organization. So there's a shared infrastructure and shared institute, but many groups have their local infrastructure by their university or different cloud providers. So there's no central control on the technology side. This is both not desired politically, because of many universities like to have their own things, nor is it practically financially viable, because the Confederation wouldn't want to fund a second copy of a lot of this infrastructure. Still, you have 20 partners and you all want to talk to each other. You have to communicate. And in Switzerland, in a country where they cannot even standardize the language, we have 4 lovely ones. How do you standardize? Well, you standardize on timing. You have a standard of the train arrives on time. So while you have lots of different cantons, different areas, you're all connected by the federal railways, and the trains are all the same no matter where you are in the country. And we try to do the same thing for data, making our data flow smoothly and on time between the different research groups, and also being there so that whenever you want to take the train, you know it's 5:09, you can just get onto it, and before you know it, it'll be in Zurich. This is because we like to collaborate. It's a requirement for the SIP members, and collaboration is, of course, visible in the amount of papers we write together, but we also need to collaborate on data. And we're starting to do this with more and more of our core data resources and some of our Elixir core data resources. For example, GlyConnect, OMA Browser, PG, OrthoDB, HAMAP, MetaNetX, UniProt, RIA, and Nextplot are some of our public endpoints where we provide a Sparkle interface to the data. This is a Sparkle interface. That doesn't mean that we have the same technical background behind it, but that we present the same API, and we try to standardize how we present the data that we share. And this is an ongoing process. But why do we do this? Well, FAIR. If you haven't heard of FAIR, well, you haven't written a grant in the last years or read your own Cubic website. FAIR is not just a buzzword. There are real technical things that you can do today to make your data fair. You might think it's not practical, But to make the data reusable, the first step is to make it usable. Then you need to make it interoperable. And to make it interoperable, you need to know what you're identifying. Otherwise, you can't even point to it. You can't say that thing. You have to give it an identity. To make it accessible, you need to make it available. So you need to look at that part. And you might be able to find it, but if you can't access it, it's very difficult to use. So beyond the political software, there's a real technical background, which I like to show how we approach it. And we approach it with using RDF as our core knowledge representation. And why do we use this technology? Well, let's look at how we've been doing bioinformatics for many, many years. This here is a schema diagram of basically every job I've been doing for many, many years. You parse, parse, and parse. You write some more parsers. That's why we were learning Perl and then Ruby and then Python. But it's the classical bioinformatics idea. You take some public data, you add your own data, and you put it in a database so you can query it. It doesn't really matter what database you're using. If you're using MongoDB or Oracle relational databases or Solr or any of the other ones, the basics hold. You write a parser, you put it into your own schema, and you load it in a big ETL transport and extraction. Never mind that. ETL pipelines. And this is the same thing is true for your own data. In the RDF world, it's a little bit different because we standardize on what the information means. So here we have the example with RDF, and this is what's true today. You have Go, gene ontology, provides their data in OWL, and also Go, it's now also in OWL. In Prod, we provided an RDF XML or Turtle from the website or anywhere else. And you might have your own data, which you might represent in one of the RDF formats. That might be JSON LD, that might be RDF XML, and triples, whatever is practicable for you. You still load it into your local database, which would now be one of the many different Sparkle endpoints. And then you can ask your questions with your query language. Doing a schema for your own data is still a requirement, but because in RDF, the schema is inherent to the data, you don't have to write a separate parser afterwards, so you can just load it from there. So you already cut off a lot of work that we used to have to do beforehand. That's no longer required because you don't need to write the parsers. That means you don't have to download BioPython to get a quite decent parser for UniProt data. No, there will be no need for that. You'll get the data in its most precisely interoperable format. Now, loading is still a requirement, and putting it in your own database is still a requirement. But actually, in the RDF world, you don't even need to do that. You still need to be responsible for your own data, your own schema, and the database for your own data. But because RDF and Sparkle brings what you call federation between databases into the mainstream, you can actually have a small database with only your data, which talks to sparkle.inprod.org to talk to all the UniProt data, not just UniProt KP, but taxonomy, UniPark, UniRef keywords, and PubMed citations. And the same is true for the gene ontology. They also are providing us with a Sparkle endpoint. And these Sparkle endpoints can talk to each other because they have a little connection. And you might have seen on the previous slides that there's little dollar symbols. In the first slide, you had $10 symbols. Second slide, you had $5 symbols. This slide, you have $2 symbols. There's a lot of savings that you can do if you don't have to integrate all the data locally, but you can actually connect to a public endpoint, to a public data provider at a much reduced cost because UniProt is very large and there are databases in the life sciences which are even larger. If you're a PhD student who can just afford a certain cloud budget, then it's really nice that you don't have to download all of UniProt, which is already getting, to a 2-3 terabyte database before you even talk about your own little database. Same is true for gene ontology and many other cases. So cost reduction is a major use case for this. But how does this work? Why doesn't the other technologies allow this? Well, it's because RDF solves a very important problem. The problem of identity. 9993. What is it? It is a number, a digits, alphanumeric string. But if you go into PubMed, you'll get PubMed 9993 is an article. NCBI gene says it's a gene. NCBI taxonomy says it's a marmot. Which one is it? Well, use IRIs. Disambiguate. PubMed.ncbi.eliminate.nih.gov 9993 is a PubMed article. It says so because that is what PubMed says that it is. And it's a really lovely new site, and it uses some RDF in there as well. And the same is true for NCBI gene. With identifiers.org, you know that NCBI gene 9993 is a gene, and you can retrieve this page, look it up in your web browser and say, oh yes, this is a gene, it has a name, it does something. And the same is true for the taxonomy. Just being able to have identifiers while long, which are precise, allows us to combine things which otherwise were not combinable. Because I have seen papers in the wild where somebody did do a join between the gene table, but actually, instead of using the gene table, they used a PubMed table, and they got really bizarre results, published it, and retracted it. These kind of things happen. That is really a painful thing in the classical technology stacks. So, what is this RDF all about? Well, it's about using IRIs to identify things. IRI is the same thing as an URI, URL. IRI allows the wider character ranges, and URL also locates, not just identifies. And the URL is just the thing that you put into your web browser. www.google.com is a URL. It's also an IRI by chance. We also still have strings and literals, because at some point you have to point to something concrete, and the concrete here is a bit of data, a string. But unlike many other data formats, we actually have language tagged strings. So you have a string, and a chien with an at of R says it's a French string. It's not just a string of characters, it's a string of characters which have meaning in French. You of course have the booleans, true, false, integers, 1, -1, floats, but also things like Gregorian year, which is saying it's a period, dates, date times, and something which is very, very special, which other technologies don't have. It's blank notes. They are a real pain in practice, but they're also something beautiful because they are placeholder identifiers. You know something exists, but you don't know its identity. Take, for example, when you're playing a murder game. Somebody is the suspect. You're sitting around your table with your friends, you're having your Cluedo in the middle, and one person is the murderer. So you'll have a blank note for the murder subject. And as you come along, you'll have clues. It says, well, the murderer has brown hair. And at the end of the game, you'll be able to resolve the identity of the blank note and say, the murderer is my friend who's sitting next to me and drinking his coffee. And this is something that is useful because in RDF stack, you will have something called AL reasoners. These are logical reasoners which basically go through the game of Cluedo for you and try to find the identity of things. So once you add more data, these blank notes can resolve to real things. Now, all of these are combined in little sentences, which are called triples: subject, predicate, object. You'll see this a lot. Some people call them statements. Sometimes you add a quad to give them a little group, but subjects are blank notes or IRIs. Predicates are always IRIs, and objects are either IRIs, blank notes, or literals. And these little sentences of data, they connect each other. For example, I love my wife. Well, I can be replaced by IRI. This one will go to the web page of my institute, which gives me a picture. It's now 12 years old, and my phone number, things like this. Dictionary.com, browse love. It identifies what I mean with love, or a little bit more. The blank note princess is basically using the syntax to say, well, this is a blank note. You don't know who my wife is. You haven't met her. And as she's quite private, it's the way it's going to stay. My wife hates this example, by the way, because she gets objectified and she doesn't like that. Now, so from all these little triplets, how do you make graphs? Well, let's say you have two triples. Use IRIs and literals. And these IRIs, when you share them, you'll share the triple connections. So on the left-hand side, let me just use a pointer. This part is one triple. This is a second triple. And these share the subject. And this second one, where it's an object in the first triple, it's a subject in the second triple. And this builds a long, big connected graph, cyclic, but directed. And with these little sentences, very small, you can build up your data structure until you end up with something like 68 billion to express what all is the data in Uniprot. And it's these global identifiers of IRIs plus the semantic standards that makes these data integrations on the fly possible. And I'll show some examples of that later on in the talk. So what does it look like? Well, triples. Here's an example from Uniprot in the format called N triples. This is the most verbose format that exists for Turtle, but it's the most clear to say you have a column of subjects, you have a column of predicates, and you have a column, or well, a little bit of deciding, of literals and objects. So you'll say there's an Uniprot entry P05067, which is reviewed true, so it's part of Sysprot. P05607 is something that has a type, uniprot.org, protein. It has been created in 1987. Uniprot has been around for a long time, and its predecessor database is Sysprot even longer. Created, well, that might be a blank note because somebody might have forgotten. Or a research and release was missed, and then we don't know when it was created. The first few releases of Sysprot are unfortunately lost. The ones in 1985. But that's not very human readable, you would say. Well, that's true. Many things are not human readable. And other things are human readable, but you still don't want to use it as your main user interface. For example, this here, Minoan linear B, it's very human readable. Not many human readers can read it anymore, but some postdocs and some professors can. And this might be a little bit like your code that you wrote before lunch. You just said, well, that looked firstly fantastic, but when you read it again, not at all. You have to have a bit more context. So people say, well, that's not readable. Let's give it something that more people can read. Well, okay, here, lots of people can read this. Some people might think that's not the right kind of language to use. So let's go for something even more popular. Lots of PhDs can read this. Is this what you want for human readable? No. Human readable is a problem for us as users, because even though a human can read it, doesn't mean that a computer can use it, or that you as a different human can read it. Now, we need to make sure that our data interchanges aren't left to the point of, oh, I could read it, so you can read it. No, that's not how it works. And we know it doesn't work that way because of practical experiences. So also for RDF, we have something which we would think is a little bit more readable because it uses more abbreviations, more context to figure out meaning. This is very important for humans, and it also reduces the size. So in Turtle, it's still the RDF. You still have subject, predicate, object all through the page. But like in a good paper, we will first introduce some abbreviations. So the base abbreviation is basically a way to say any IRI that we're going to construct is going to start from here. And the prefixes are really a way of declaring an abbreviation. So RDF is a abbreviation for http www.w3.org.1999/02/22/RDF-index-ns hash, which you don't really want to repeat all the time. Just say RDF. So we look at the little part where we say, oh, we have three triples. We're still talking about this P05667 RDF type protein, and it's an up protein, so it's from Uniprot. It's up reviewed true and upcreated 1987 with an XSD date as data type. And this is just a very useful way of giving the data. RDF is a knowledge representation which doesn't care about its serializations. There are other formats. So you already saw in tuples and you saw total. There's RDF XML. This was the older standard because before the JSON hype, at some point, it was all about XML. XML, 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 and style shields. Really, you cannot remember this, but it happened. So it's all the standard from 1999. Now it's all about JSON. So you have JSON LD, and it can be used to map RDF into JSON, or the other way around, some JSON into RDF. It's very appealing, but it is really tricky to do right. And I've seen quite a few people thinking like, oh, it's so simple, and then actually not representing the knowledge that you wanted to do. There's also something called RDFA, and this is for embedding some RDF in HTML. And if you ever looked at, for example, Facebook Open Graph Protocol or the Twitter equivalent, this uses RDFA. There's also things like HDT, which is called Header Dictionary Triples, which is a very compressed way of talking about RDF data. But at the same time, you can query it. So you have these different formats for different use cases. If you're making a web API, or which you also happen to want to make RDF at the same time, JSON LD is a very good choice. If you are doing schema.org markup in your web pages and you don't want to have bloat from too many literals being duplicated, RDFA is a very good choice. If you want to have a big download file from for big downloads, then you want RDF XML because it has self-closing properties. So these kind of format changes are useful. But the nice thing is that the same data can be converted automatically from RDF XML to any other format. So RDF XML to JSON LD and back again is lossless. There are some edge cases which are, what is representable in JSON and what is representable in XML, which is mostly about lower ASCII codes like the bell sound. Yes, that does not round trip between different areas. I see a question from Josiah. I did not put a JSON LD example snippet in the talk, but if you look at schema.org, you'll find many. And that is a very nice project because if you're marking up your web pages so that Google, Yandex, Bing, and all the ID Spider can really figure out what are you talking about on a web page, then you'll see it. For the people who don't know schema.org, schema.org is basically technology which allows Google Maps to survive. It's a little bit of RDF snippets that you put on your sushi shop website and it says, I'm a sushi shop, I'm open from 9 to 9, and this is my menu. I have macro rolls and it will cost €2 and these kind of things. And use a little bit of RDF snippets for that. And even though Google has spent somewhere close to $20 billion over the decades on improving natural language processing, just the shop saying, I'm a sushi shop, I'm open from 9 to 9, really helps. And it makes Google Maps really possible. So, zip RDF. Interoperability has been doing it for a long time. 2004, we were way ahead of the hype curve. And when I started at Interoperability, I was really thinking like, oh, really? Yet another data format? Why? But over the decades, over the years, it has been taken up by other resources. And the breakthrough take-up was really in 2014. And I'll explain later in the Sparkle project, but that's when basic federation was introduced. And that is really the key use case for us. On the other hand, we have always been linking Uniprot to other databases, and so have all the other databases of SAP. You will all have cross-references. And for Uniprot, it's more than 200. And we also need to identify all the things. If you never really realized, but there is a little regex for the Uniprot accessions, which was painstakingly designed to make sure that no Uniprot accession could ever be the same as an ENA GenBank accession. So these are the old things that we're doing from the 1980s. But at most this time, we just want to use IRIs. It's much simpler. So that's nice, the RDF. So we can represent our data, but we need to query it. And we would like to answer questions with our data. That's why we were collecting it in the first place. So nice thing about Sparkle is that there's a lot of different implementations. So different implementations come for different price tags. Some are open source, some of them are very much closed. Some are cloud providers, some are in-house by pharmaceuticals, Apache projects, such as RIA and Gina, or Eclipse projects like RDF4J. There's also approaches for Python and any other major language other than C++ in the open market. Nice thing about different implementations is to implement the same standard, so you can switch. We have used and evaluated most of these at some point in their existence, just to see if they will give us a better cost benefit. And it's nice to be able to evaluate them because we have the same queries and same data. So all we need to change is which loader do we call? Do we call iSQL loader, or do we do something from Oracle side? It was very cheap to try out 10 different stores and figure out which one brings the most value for our money. And that means we can actually argue to our funders and say, well, we tried 15 different things that cost us 2 months of work, and at that point, this one is the cheapest, so that's why we're using it. Very different from how many other people say, well, we're using MongoDB. What else did you try? Well, MySQL, that's completely different. If you want to move from one to the other, it's basically a software rewrite. So Sparkle basics. So you remember your little turtle from a few slides ago? And since 1.1, RDF 1.1, it looks like Sparkle. So Sparkle and Turtle, they are going very close together. I'll show a little example. Take the Turtle example that we had earlier. You have the base UniProt, you have the prefixes in the same way. You still have P0567, and you say it's a protein. Well, instead of asking UniProt for this data that we already know, what do we do? Ask, are there any other entries that were created on that day? Well, yes, we introduce a variable. The variables are with a question mark, protein. If you're very much in the pro mode, you're allowed to use a $sign, or if you're in finance, $sign instead of a question mark is allowed. And that's the first step. Second step is you add a little select anywhere. To be honest, the where clause, the where word is optional, but it's very nice to be able to see it. I'm a person who writes in shouty case, very old style SQL, so that's why selecting where are uppercase, but other people don't do that. It's not required. And that's it. That's a Sparkle query. You had your data, you changed it into a variable, and now you can use it to query data. You can actually take this, copy it over to the sparkle.uniprot.org website, and this will run, and it will give you an answer. We also have more than one way to give answers. Select, which is what you just saw, gives a table. So this is pretty much what you get from a relational database as well. Nice thing is it's immediately over HTTP, and you get either JSON or an XML per standard output. So the JSON is really easy to use in little web scriptlets. Or if your endpoint like the UniProt or one is nice, it will give comma separated values or even Excel tables, but everything in the Tableau form. Construct actually is give me some more triples. So it's basically take a graph, make a new graph, give RDF from the RDF. This is useful for when you're doing data transformations. And it actually for the Sparkle update languages, construct, you replace the word construct by insert, it will actually insert the changed data. Ask if you just want to know true or false to the answer of the questions. And there's something called describe. It's underspecified for a good reason. You shouldn't use it in programs, but it is very useful when you're trying to discover how an external data set is constructed. You just say, describe this IRI, and it will show some relevant triples. And from there on, you can navigate through a database. So you can query data, but that's what everybody else can do as well. There is no big value add of using Sparkle over RDF, over SQL, or over any of the other competing technologies. The one thing that we bring to the table is called federation. And federation is that when you ask two databases to work together. And it really is just a very simple part. You basically introduce what we call a service clause. It's a little subclause. And you just say, hey, database, for this part of the query, go talk to that other database. And when you get that answer, use it as if that answer was actually already stored in your database. So here we're combining uniprot.org, sparkle.uniprot.org, and sparkle.readable.org. So Uniprot has been using RIA now for 2 years to annotate the catalyzation of reactions. How do enzymes really work? Because RIA is a very nice database with chemically pH 7.3 balanced reactions for charge and mass. So then now we have in Uniprot, we say, oh, this protein has that catalytic activity. But if you want to do then some biochemical questions like, well, what are similar chemicals to that chemical that we had in Uniprot? Well, then you use the RIA database. Of course, historically, we could have eaten RIA into Uniprot, and eaten is the right word. It has happened in the past that Uniprot has integrated even sometimes very small pieces of data from an from an external database, and then the funders go like, "Oh, well, all that data is now in Uniprot, so we don't need to fund database number 2 anymore because Uniprot already has it." And then Uniprot is like, "Well, we integrated it, but we don't really know this data because it's outside of our example." Um, and that gives these kind of problems. Now with RIA being a separate database and not fully integrated, RIA has its own, stands on its own, has its own use cases beyond Uniprot, and it's very much separate. Uniprot uses but didn't integrate. Some of the databases we just are never going to integrate. Uniprot is relatively well funded, but we could never afford to integrate all the patent data. And to be honest, European Patent Office has enough of its own business that they don't care about Uniprot. So it's really nice that European Patent Office also has a Sparkle endpoint. And because we're both fair resources, we are interoperable. We can reuse each other's data. We can cross-query as if they were one databases. Small identification hiccups to the side because Uniprot has a little bit of string mangling to do to get the right accession from the APO side. And this is the kind of thing which gives power. It's not an interesting query because we don't have that many patent citations in Uniprot, but it really shows that just because we use the same technology and this technology allows federation, we can have databases talking to each other. While in other systems, we would have had to download significant amounts of data from one system, ingest it onto our own system, write parsers, write loaders, put it into a database, pay for the full storage cost and the maintenance cost of all these things, which we all know how to do. We all know how to write parsers and load databases, but at some point it gets very expensive. Now we can actually do these queries and we can see, is this an interesting query? Can we find the patents which were once granted? Because you will actually find out there's quite a few patent citations in Uniprot where the patent was never granted. So it gives you a bit of information of what is relevant or that the grant patent is run out. So it's one area of looking into, oh, can we do now more things than we could 5 years ago, just from a legal side? So federation, it's not perfect. There are issues, different implementations, bugs add up. You have Sparkle 1.1 compliance, downtime. You have 99% uptime and 99% uptime, while 2 of them together have 98% uptime, and so onwards. Also, the optimizers for federation are quite non-existent in the standard implementations. So going from RIA to Uniprot or from Uniprot to RIA, but otherwise the same query can give runtime differences in, well, order of years. The distance between endpoints is of course also a big issue. If you're bringing everything in-house into your own data center, well, the latency will be in the milliseconds. If you're talking between using Uniprot.org and let's say AliDB from Japan, well, you're talking about 500 milliseconds round trip in the best of cases. Plus HTTP is set up per packet, so you'll have just from this distance humongous latency and runtime explosions. Endpoints change all the time. The number and kind of triples changes, and implementation changes. So what was fast now might become slow next, or more often the case, what used to be slow is now fast. So I see a question regarding Wikidata. So there is GeneWiki, which takes some part of UniProt RDF and integrates it into Wikidata. There's a bit of the issues between licensing. Wikidata is, of course, CC0 licensed, and UniProt is CC BY licensed. That comes up more than anything else. So in the Wikidata side, when there is a human gene, you will have the UniProt IRI in the dataset. There is not currently a cross-link from the UniProt side to the Wikidata side. If you don't know, Wikidata is the Sparkle data side of Wikipedia. So it's nice, but Sam, bam, cram, my data is too big. I can't afford to have a second copy, especially not in a large database. I need to have it all crammed onto my cheap tape drives. And to be honest, there's lots of tools that are designed to use that exact data set, right? So if all your tooling is SAM tools based, then you don't want to duplicate your data into the Sparkle endpoint because A, it's expensive, and B, you have to duplicate it because all your existing pipelines are still using it. Well, actually, it's quite trivial, to be honest, to implement Sparkle views on existing data. This might not always give you the most performant results, but hey, it gives you the same kind of capabilities without having to go and buy more hard disks. And to be honest, when you're still evaluating it, it's really a nice approach. So the nice thing of all the implementations of Sparkle engines out there, or at least open source ones, for each of the languages, and that's true for JavaScript, for RDF-lib and RDF4j, for Ruby RDF and many others, there's just one method that you need to implement. And the get statements from the Java one is the most prototypical of it. It's just asking, give me the statements with these subjects, these predicates, and these objects. And then predicate, subject, predicate, object might be no. And then it says basically implementing with the variable. And the rest of the magic is done by the Sparkle engine. So that's the only thing that you need to implement your translator. Other cases is, well, I already have a relational database and, nicely tuned Postgres SQL database, and we have all our data pipeline set up, and we don't want to switch technology stack. Well, there's something called R2RML. It's a W3C standard, and there's different implementations. This is just two of them. For example, OnTop is quite popular, and that's what the BG databases use in the SIB. And it basically takes a little translation file, and then it gets a SQL query, and then it translates it into it gets a Sparkle query with a translation table, translates it into SQL. So if you have an existing SQL database, now you have a Sparkle database. So without further cost in storage. It's really nice, and we'll be doing a talk about this in a hackathon at Elixir Biohackathon in October, I think it is, if we get to travel to Spain. And there's many commercial implementations as well, and such as from Oracle and Stardog and many more, which allow these kind of reusing existing infrastructure. And that's really powerful because that means you don't have to buy something new just to test it out. If 3 years later you say, well, Sparkle's really good, well, you can drop your relational database, or maybe that's 10 years later down the line. But just to get that capability, you don't have to invest in humongous amounts of new infrastructure. Now, a little example, there's something called OGI, which is variation genome graphs today. So we're talking about graph data structures, but for genomes. OGI is extremely memory efficient, and it deals with mutable graphs. It's all in C++, and it's all succinct data structures. So these are somewhat compressed data structures. Now, it's really nice, and it's part of the VG, the variation graph team world. And already a few years ago, we did a VG ontology, which basically saying, well, this is what a variation graph genomics would look like if it was translated to RDF. Now that there's a Python library for OGI, you can actually use the RDF for RDFlib library from Python to wrap these OGI objects and pretend that it's a graph database, as in a Sparkable graph database. It introduces IRIs for everything that is inside an OGI file, and all these IRIs are only 10 pointers to the things that are actually C++ structs or objects. For now, it's read-only, but it allows us to ask all kinds of questions of OGI files that you wouldn't do otherwise. So you think, oh, that must be really great. No, actually, if you look at it, it is, well, 600 lines of Python without the comments. It's Sparkle 1.1 and now also federated queries. And there's no extra data storage. The whole database is just the OGI file. So if you take your, let's say, the COVID public sequences, that's a 50 megabyte file with about 1,400 viral genomes, coronaviruses. At the same time, Spudgy brings a little bit differences to what OGI brings by itself. It has two views to the same data. We have used an ontology called Faldo, which was also used in Uniprot and Ensemble RDF and many others, to give the linear classical view of sequences. It's a line, there's a begin and there's an end, and then it deals with all the things that happen in biology, like, well, actually it's not a line, it's a circle, and, well, you have a gene, but the gene is longer than a chromosome. All these kind of things was dealt with by Faldo. Other side, you have VG, which is the graph, where you have elements connecting all together. Spudgy allows both of these views at the same time. So depending how you ask your question, you'll go in from a linear view or from a graph view, and you can combine these as you wish. And that's a nice thing that OGI by itself doesn't have, because if you want to do that in OGI, you need to write a lot more C++ code to actually give the linear view on demand. So Spudgy in practice, at the SIB, we did a COVID-19 Sparkle endpoint with the biohackathon group as well. It already has more than 1,300 SARS-CoV-2 genomes. Sorry, my apologies for the typo there. It doesn't only have these genomes, as in the graph structure. It also brings in all the annotations from Instack, which was given by the submitters, Uniprot, Nextprot, PG, RIA, and other SIB resources. And you think like, oh, that must have been quite inexpensive. No, this was less than 1 week work full time. And that includes the styling and introducing the website and the pipelines to get it there. And that really shows that because we're already pre-integrating between Uniprot, Nextprot, BG, RIA, and the RDF representations done by the DDBCLS in Japan for GenBank, DDBJ, and ENA, we can quickly combine all of these and actually get more insight. So we can start to ask questions like, given this gene that we have annotated in Uniprot, which of these SARS-CoV-2 genomes have exactly the same gene? Which ones have share some nodes with these ones which are exact in the VG graph, but don't have the exact active site annotation? You can start asking these kind of questions. And that is a real power from being able to integrate the data cheaply. We didn't have to write parsers for this. We didn't have to change much of the data. So it's very simple cost. It's running on a small server, 2 CPUs, 2 gigabytes of RAM. And if there's more demand, we add more CPUs or more RAM. So to leave it off a little bit, you too can join us with your own RDF or a view that just pretends your RDF. The key things are one IRI, one resource, one thing, one identifier. The format is not so important. You've seen many people who are using RDF XML because they're starting with an XML data format, or JSON LD because they're starting with a JSON format. Reuse ontologies that exist, existing schemas, but only start doing that once you understand what your own data really means. That is one of the big hurdles that we always have. Like, well, what does this column 16 actually mean, and why does it sometimes have 2 values and sometimes 3 values, and what do they all actually indicate on a biological sense? What do I tell to the end users? So kind of documentation. Now, This is the end of my talk. I hope you enjoyed it. The Swissport group, of course, makes all of this possible, especially the Interplot Sparkle endpoint, the RIA and the HAMAP ones. Swisslipids will have a Sparkle endpoint soon, and for the COVID fight, Viral Zone and ProSite. HAMAP and ProSite are scanning tools, so you might not think like, oh, these are very RDF reliable, but actually all the HAMAP rules for annotations are expressed as Sparkle queries for you to use locally. So thank you for your time, and I hope you enjoyed the talk. And I'm open for questions.
Yes, thank you so much. Please ask any question you like, and we will stop the recording in a bit, but leave the Zoom room open for you to keep chatting.
From GCI Seaman, in the wild, how do you handle people making redundant ontologies for the same concept? You don't. The thing about people is they do what you want to do. So what you do is you map ontologies. You say, oh, Professor X's class is exactly the same as Professor Y's class. And that is how you deal with it in practice. The fact that you make redundant stuff, it's like people making redundant databases. You know, that's what people do. Some people, you might be able to get the data to work together on a technical level, but on a social level, Professor X will always hate Professor Y because what happened 20 years ago in grad school. Social problems, stay social problems. Yes, you can have a database service of redundant concepts to augment federation. And at some point, identifies.org actually ran one where they basically translated IRIs on the fly. And the OLS, EBI OLS might actually do something like that. But at the moment, there's nothing super. Aberal from the KAUST University does this quite a bit because the reason about concepts being identical, and that is available via Sparkle.
I have one question. Maybe I speak up if you if you don't mind. So you had that one of your last slides with the SARS-CoV-2 example where you argued that you came up with a Sparkle endpoint to bring all the data together. And I'm interested in the second dark bullet point, extra cost, 1 week of work. So is that 1 week of work for you? Is that kind of put together by the different partners that need to put in work there to come up with a Sparkle endpoint? Or how is that? I mean,
No,
is
that's
it
like
central work or is it decentralized work that is summed up in 1 week?
Yeah, so it's like 40 hours over all the groups,
Okay.
mostly about, oh, which is the data you want to extract for the Sparkle smaller, because you don't want to have everything integrated. It was just what is relevant here. So that's the up-to-date Uniprot pre-releases, the most interesting Nextbot entries, the BG parts.
Okay.
And so yeah, it was like 40 work hours from all the different teams, and that includes styling, going back and forth about what kind of banner do we put on. So that's a very low cost, I think, for it. I see a question from somebody. What is Neo4j? Neo4j is a different graph database. They are going from the property graph area, and that is really friendly for developers, but it doesn't actually solve the problem of having federation. It's basically a nicer relational database for many people. They have pre-announced that they will start supporting RDF and Sparkle soon, so I expect more news from them on that, but that's just a commercial side. Are there drop-in visual browsers for knowledge graphs? Yes, there are. Some of them are really nice. Some of them are really expensive. And I'm not the best expert on them. And they change over time, what is nice. Also, we've seen that visual browsers look really, really great in small demo sets. But once you actually hit it with real data, you just get well, balls, lots of balls all over the place, balls. They bounce and they lift, and they don't actually give you insight because the graph is just too connected, which is definitely the case for the unipart type graphs, where it's just very quickly um, a useless thing. Different question is, are there going to be variation graphs standards? Well, there's lots of standards already, which is what we do in the field, right? So there's GFA and GFA2, and there's definitely something coming from Hangli as well. I'm not sure if that's the same, but they're very much focused on the data itself, right? So they're only looking at the variation graph and no further than that. And the moment that you actually want to annotate, what does that mean? What are the parts of the variation graph is about a gene? Then you need to put into pointers and hash maps and things so that you can actually store all these things that you want to add. And in practice, the variation graph people have been so focused on compression that if you start adding these kind of pointers and these hash maps, then basically your data structure becomes a generalized data structure, and none of the compression technologies work anymore. And you can't actually store the data that you need. So for the pure graph topology, there are approaches, but the only thing that brings graph topology plus everything else is the RDF ones. And as far as I know, only VG RDF is the only standard, well, proposal there. Yes. From Simon, yeah, we have 60 plus billion triples. So on the front end, we have two independent nodes, one in Geneva and one in Lausanne for resilience. They're in universities. Power cuts have been the major source of downtime. And these are quite old now, 2014. You were ordered in 2013, arrived in 2014. 64 core AMD Barcelona machines with a quarter terabyte of RAM. At the time, it was about 30,000 Swiss francs, so quite affordable. And the only thing that we've upgraded over the years is the SSDs inside. They're actually on a very slow SATA 2 bus, but there's SSDs in there for speed. And currently, at the time, we went for 1U units, pizza boxes, and we've had to update mostly for the disk size. Now we use VDO, which is a nice lower level stack underneath the file system in Red Hat, which compresses it. So we'll have those machines going a few more years, and then we replace them. They're already getting to the point where the electricity cost is getting significant, as in the amount of heat that you produce. This is very good for the read-only kind of queries. And with Virtuoso, which is very columnar-based, it survives. When we go beyond, well, 200 billion, we might change the tech stack to go something a bit more federated, just more distributed inside the local cluster. But it's a very affordable approach. We have a few, around 1,000 to 1,500 people, sometimes even 2,000 people using the Sparkle endpoint, writing their own queries. When we're using it to prototype some of the new features on the normal Unipart website, we've had peaks of 115, 200,000 users, unique users a month, or unique IPs a month visiting the sites, generating millions of queries. But those are very pre-canned, so they're very easy to cache. So we definitely have a very good Apache load balancer in front, multiple ones, with a small cache there. Architectural Proteome still the largest part of Unipart database? Yes, that is the case. Most of Unipart's KB is still bacterial proteomes, and that's not likely to change anytime soon. How do we deal with redundancy? So there's what we call proteome redundancy and of course identity redundancy. And one of the problems is, so it's already highly reduced, right? It's different talks from the Uniprot group that you'll find. It's not exactly my department, that you see that you start with 2 billion sequences in GenBank, compresses down to 600 million, 300 million sequences in Uniproc, and that gives you, after redundancy, 160 million sequences in Uniprot. So if the bacterial genome gives the same identical proteome, well, it disappears. If it gives a very closely related proteome, it will disappear by not including it in Uniprot KB, but only having it in Uniparc. So yeah, basically we try to have data that actually tells people something, because you might be able to grab all the data that is existing there, but if it's just the same kind of data run through the same kind of pipelines, it doesn't tell us anything new biologically. And if it doesn't tell us anything new biologically, then it's just noise that makes running a blast more difficult, or a text search more difficult. So we're still very much looking at removing data that doesn't add value to our end users. Regarding the infrastructure talk, there's actually, if you look for my name in YouTube, you can find all the talks which goes through the infrastructure that we use for the Sparkle endpoints in more detail. And Josiah's remark is correct. Graph genomes will reduce redundancy by not looking at it as sequences, but at sequence spaces to actually see what is the variation and what is the biological consequence of the variation. Having more sequences is not so interesting. Actually knowing what the variation in the sequence space indicates biologically is where the next interest is. And that actually means that this is very much a personal opinion. We will start to have to think to go away from the gene-centric and protein-centric view as in single pieces of data. And we actually have to look at them in the wider context. I'll leave it open for 1 more minute for more questions. And then we'll allow the Zoom to go to bit to one-to-one talks. From Simon, if we had protein sequencing, what is the challenge that I would expect on my side? Hard disk space. The budget for hard disk space is definitely not ready for high throughput protein sequencing at the rate that ENA has been doing over the years. Other hand, we might get a lot more PTMs, and that would be very nice. That would be very enriching. Other hand, when we had real protein sequencing that is really done, and really, we might get rid of significant parts of Tremble, because if you have the real thing, then you don't have to need the predicted translation. So we'll see what that does. But most of it is disks, more disks. We would need so many more disks.
Okay, if there are no more questions for now, I will stop the live streaming, but leave Zoom open, and then we can make breakout rooms, and you can talk to Jerven in more detail about your projects if you like.